a big pleasure and honor to speak at this conference in lovely ESI in lovely Vienna. And I think at the end of the first week, it's the first moment to thank the organizers for their work. So thank you very much. And where's Cornelia? Ah, okay. Okay. So I'm not that infinite dimension in that speech. In fact, it's a little bit contradiction because many years ago I worked a lot in infinite dimensions, and then I turned to finite dimension. In fact, the subject I will speak about is to avoid infinite dimensions. I will explain more detail during the talk, and but the infinite dimensions come again from the back door, so it's not completely avoided. So let's give a short motivation on it, which explains this better. So if you look at a classical field theory, in naive sense, you can say you look at maps from an n-dimensional source to another manifold, and you have an action or Lagrangian function goes to R. This might be a section space, but basically it's this. And you look at the critical points of this. This yields Euler-Lagrange equations. And if you want to quantize this, then there are basically two approaches in field theory. So either you go to path integrals, definitely infinite dimension, but suffer of a lot of problems with the very definition, I think. In very few cases it's well defined. And the other approach is that you hope that you might reformulate this in a vaguely set Hamiltonian way. So you go to something like P star of this map space, and you claim that for some strange reasons you have such commutators on the components. Phi is a map itself, and this is the extension to the cotangent bundle. And you hope that by what the physicists call covariant quantization or canonical quantization back to the 20s, that if you write a hat on everything, then you get I times H bar beta. So both methods go to infinite dimensions, but both methods are very little rigorous from a mathematical point of view. And a couple of years ago, I discovered that there might be a way to avoid infinite dimension, at least on the classical level, by going to what is called n-plectic geometry. So in this case, avoid infinite dimensions. Slightly heretical. You look at the bundle, in this case just sigma n q or sigma n. And then you go to a sort of cotangent bundle, which is, I don't want to go into details, which is the n-fold multi-cotangent bundle, and it's slightly restricted, but this is not so important for this talk, what it exactly is. This is, if you want, this is isomorphic to some kind of dual of jet spaces. If you prefer to think that there's a Lagrange theory and then you have a Legendre transformation, but I don't care about this point of view. I want to look on this side. And I call it maybe M of pi. So this map is pi. It's a bundle associated to this. And the interesting about this is that there is a canonical N form and a canonical N+1 form. I also don't need details. It is tautological S in the well-known cotangent space case. And of course, you have d theta canonical N+1 form. And with this N+1 form, you can try to mimic what you do on a cotangent bundle in the symplectic case. And you get what I call the Hamilton-Redonda-Weil equation. So I write it down for a function. H is a function. And if H is a function, you can calculate that this is an n vector field. So this is like the case n equal 1. And then you have what I call dynamical gna, which is iota psi lower star x gamma x omega in psi of x equals dh psi of x, where psi section strange thing about green blackboard is that green is a good color. Right? Is a section, and gamma is a co-volume. On sigma n. And in good cases, this equation is in fact equivalent to the Euler-Lagrange equation. And in fact, if you can think this is just S in the classical case, is just reduction of order. Euler-Lagrange equation typically are second order if the Lagrangian depends only on the fields and the first derivatives. And if you make reduction of order, then you get first order. And this is a first order equation. In good cases, it's equivalent. This is not my point, but this justifies why it comes on naturally from physics. And the question, one, of course, is sort of forced to think about is what happens to quantization? I mean, because it would be very nice if you have an algorithm or almost an algorithm to go from a classical field theory to a quantum field theory. So in the case n equal 1, this is just symplectic geometry. You have a lot of algorithms. You have deformation quantization, for example. In certain cases, you have, again, this canonical quantization, and I'm interested in geometric quantization. And the question is, what happens if n is bigger than 1? Okay? So I want to discuss the case n bigger than 1. Okay. And mainly, I want to discuss the case n equal 2, because it's getting rather involved if we write down everything. If you're really good with categories, maybe you can do every n at the same place. And everything is just an n category and whatever, and you see what it is. But I write it down as classical objects, as differential geometric objects, and then even the case n equal 2 gets involved. Maybe due to my classically trained brain, which has difficulties to say, okay, we take the n categorical version of everything, and then it's fine. Okay, so I stick.
So like in this case, is h a function on the dual of the jets you wrote?
H, in this case, H is simply a function on this object C on M of P. Well, in more general, there's something called a Hamiltonian section, but it's a bit of a pain in the ass. And if you assume that sigma is orientable, then you don't need a Hamiltonian section, then you can work with functions. Of course, you can take a form here. If you take a form, then you don't have an n vector field, then you have a k vector field, and then you have lower dimension. You have all dimensions from 1 to n. You have also lower dimensional equations. But if you think in terms of field theory, the most interesting thing is an n-dimensional source. If, for example, you take a form of degree n minus 1, you only have a vector field, and this would be something like fluid dynamics. Then you had just flows. Okay? But the interesting case for field theory is to go to the maximum dimension and to look for maps psi which are defined on an n-dimensional source to really distinguish from particle mechanics. This is the most extreme case. In both the most extreme cases are fluid dynamics in a certain sense. It's a one-dimensional source or n-dimensional source. And of course, n-dimensional source is a field theoretic picture.
Yeah, in your DH, you have this subscript of like psi of x.
It's just a point. I don't know how you want to write it.
Yes,
It's the one form in this point.
In the dual of the jets, right? Because like psi is a section.
Yes, psi is a map here. Maybe green was not so good. I'm sorry. There's a section here.
Yes, and you have like omega again, like which is like n form.
N plus 1.
Sorry, n.
Omega is n plus 1.
Yeah, fine.
This is n plus 1, this is n, so it's 1, this is 0, so it's 1. Okay.
And like a gamma is like pushed forward.
It's a covolume, so this gamma is a non-vanishing section of the n vector field on the source.
Yes, and the psi star is like pushing forward this.
Yes.
Right? Okay.
Lambda wedge of the tangent map.
Yes, perfect. Yeah, thank you very much.
Okay, so to get used to it, I will speak a little bit about the two-plectic zoo. Because you might think that either this is rich or this is not rich, and it's rich. So I give some examples. Okay, I give the general definition. I mean, it's a little bit boring. I always give this definition, but not so well known maybe. M, a manifold, omega n plus 1 form is n-plectic or multisymplectic of degree n if omega is closed and non-degenerate in a weak sense, a relatively weak sense, if you contract omega with an element of the tangent bundle, then the vector was already the zero vector in his fiber. Okay? you want, this is one non-degenerate. You can also consider two non-degenerate. You can put in two elements and so on. But typically, one non-degenerate is what you can expect, and even two non-degenerate is typically not true. So, some examples. So we had this this example there. So if you have sigma 2 n equal 2 in the motivating example, then you take a threefold with a volume, also two-pectic, or you can take products of these kind of manifolds, or take, let's say, to make it easy, let's say it's m, the real dimension of m is 6, and j is integrable with almost complex structure. And Calabi-Yau, so you have a non-vanishing 3 form in the holomorphic sense. I don't know how to write it. 3-0 if you want. Non-vanishing and closed. I call it big omega. Without zeros. Then you can look at the real part of it. Not completely necessary that it's integrable, but then you have to refine the conditions. It's the easiest case. So all Calabi-Yau manifolds do this. And what else? You take a symplectic manifold, and you take a one-dimensional manifold, R or S1, then n times R with eta wedge dt, or the pullbacks. This is two-pectic. What this Fourier forms, Fourier did his PhD with Desaulniers or Molyneux in Montpellier in the 70s, a sort of a lost PhD. Nobody considered it. And yes.
The one-dimensional what? Manifold?
Well, this is, let's say, R or S1.
So n times T. Yeah, n
So
times.
here is n cross.
Okay, excuse me. You're right. And then maybe more interesting example is you take a semi-simple Lie group. And you define a 3 form, the neutral point, by Killing form of the bracket with zeta on the Lie algebra. And then you take the left invariant form or the right invariant form with this variant. It's automatically bi-invariant, and a bivariant form is automatically closed. So omega bi-invariant tangent. So this is one form. Understand that for each form I search for a French title. Not necessary. It's even more general. You take what is called a perfect Lie algebra, okay, with a non-degenerate bi-invariant scalar product on the Lie algebra, and you do the same thing. There are examples which are not even non-compact semi-simple, which are perfect and have this condition. But of course, the typical case is a compact case. One thinks of this. And the last example, I was talking in the summer. I take the imaginary octonions. They have a vector product. This is R7. They have a vector product and a natural three form defined in terms of this. I take I don't know how it's called in English. In the three-dimensional case in German, it's Spartprodukt. What is it in English? Triple product? But we are not in dimension 3. Huh? We are in dimension 7. Okay? And you can embed the 6 here in R7, and you look at the pullback of this form. And this is a closed non-degenerate 2 form, 3 form. This is very weird because, for example, this has a potential. Yeah? It has a potential, and this has only a finite dimensional group of automorphisms, which is G2. Yeah? It's really the opposite of symplectic. You have very few Hamiltonian vector fields, yeah? And you have a compact manifold, and your form has a potential. So all your intuition from symplectic geometry is wrong. Yeah? Of course, you know that S6 has no symplectic structure by cohomological reason. So the cohomological reasons which apply against symplectic structure do not apply here. It's the 3 form, it's closed, so it has a potential, but I don't care, it's possible. Okay, you see this exists in nature, even some funny examples. And now I want to recall what geometric quantization, or let's be modest, prequantisation does classically in the symplectic case. Of course, everything is from Souriau. You look at the literature, you see that Souriau is well before Kostant, and Kirillov do not have all the things Souriau had. So it's democratic. You mention also an American and a Russian. So there are 2 fundamental theorems. I was tempted to call it A and B, but it's a little bit arrogant. So the first theorem is M omega symplectic, omega integral, an integral form. Calculate the integrals, they are integral, or you look at check de Rham, it comes from Z, or you look at singular, it's in Z, whatever. Then there exists a bundle, which is a S1 principal bundle. With a connection, which I realize via a connection 1 form. Connection 1 form is a form on the total space. Maybe there's an I times real forms. Such that, if you look at the curvature, but this is an abelian theory, so the curvature is just dA. This curvature is minus 2pi. And this thus, a fortiori, omega is a first Chern class bundle. And the second theorem says something about observables. So what are observables in a symplectic theory? One considers that the C infinity function on M are the observables. This, of course, you can discuss. I think that observables, they are some kind of measures on M, if you want to observe something which is smeared out. But traditionally, as observables, you simply take the C infinity functions on the manifold, and since this is symplectic, it's Poisson, so you have a Poisson structure on the observables. And the second theorem says the prequantisation map Kostant and Souriau. I will write it down. Goes from C infinity Poisson structure to symmetries of P with A, which is simply the vector fields in the total space such that LXA equals 0. So this looks a little bit insufficient, but this condition implies that the vector field commutes with the S1 action. So it preserves the fiber bundle structure. So this is okay to call this the symmetries. And the map, well known. You take the Hamiltonian vector field associated to F. You take the horizontal lift with respect to A, and you add 2 pi I q upper star of F. This is now a function on the total space times Z. Okay, I have to explain where everything lives. X iota x f tilde xf in omega equals df, and Z is the Euler field on the total space P. So if you want, you have this fundamental action of S1, and you take a generator of the Lie algebra of S1, and this gives you the vector field which generates the S1 action. And nice blackboard.
Equals Q star omega times some constant.
Yes. Very, very nice remark. I forgot a couple of stars. Yeah. Oh, thank you. This is important remark. Some small remarks. Okay, C infinity M together with a Poisson bracket are the classical observables. This algebra of vector fields acts linearly on the set of functions from the total space to C invariant by S1. And this is the same as the section space of the associated C bundle. If you have an S1 bundle, you can associate a C bundle. So this is gamma C infinity M L, where L is P times C divided by. You can vary the action to go to L tensor K if you want, so you have also the action spaces of the higher powers. So this is typically the pre-quantum, linear pre-quantum space. And maybe I put some last remark here. So this is pre-quantization. And in the classical case, you have, you can go beyond it, quantization, geometric quantization. So you have to add two ingredients, at least. One ingredient is what is called a metaplectic structure. The metaplectic structure is something like a spin structure. You go to recovering from the group SP to a covering of the group SP. And I don't want to go into details. The point is that this allows unitary structures on this space or subspaces of this, which allow certain what is called a pairing. And this pairing is between what? This pairing is between differently polarized section spaces. So another notion which is important here is a polarization. A polarization is a subbundle of the complexified tangent bundle of M, which is omega complexified Lagrangian. I don't want to go into details. There's a small obstruction of this, this is a finite covering, so it's some Z cohomology class, which should be 0. This is a rather mild condition to have such structures. And there is a finite or countable choice of them. Finite. So this is not a very big problem. On the other side, polarizations, you have a lot of polarizations, and independence of polarization, I think this is not proved in the whole generality. Certain polarizations you can pair up, and with this metaplectic structures, then you get a pairing between them, and you can show that they give the same result. And what is a quantization in the end? In a slogan is a subalgebra of the observables act on a subspace of the section space. People from deformation quantization, they don't like it. They like the opposite. They like to stay with everything. But if you discuss with physicists, typically they have a Hamiltonian they like, and they have a symmetry group or some group, not necessarily a symmetry group, maybe a group such that the Hamiltonian is collective with respect to the group, so it factorizes over the moment map. So they have a certain Lie algebra plus a Hamiltonian, and this is what they want to quantize. They don't want to quantize all functions typically. They are not interested in this. What they are going to want, what they want is quantum integrability. What is quantum integrability? Quantum integrability means you have a set of operators which commute, and the common spectrum has one-dimensional eigenspaces in the end. So you have what is called good quantum numbers. You can really localize wave functions by a finite number of quantum numbers, and there is no ambiguity if you give the quantum number. So that's the optimal situation for them. And this you can typically achieve or not, and if you can achieve it, you can achieve it with a subalgebra. 5 minutes, this is not enough. Give me 5 more. So what do I want to do? I want to generalize theorem 1 and theorem 2 to the two-plectic case. Yeah? That's the goal of what I want to explain. And it takes only 30 minutes, I think. So okay, I start to explain it. So what do you have to replace? You have to replace the S1 bundle, okay? You have to replace the observables, and you have to replace this Kostant and Souriau mapping, okay? And there's a subtle point in the Kostant and Souriau mapping. The Kostant and Souriau mapping is an isomorphism. So all these you have to replace, and I will write down the two theorems, the analogs of the two theorems, and just by hand waving, I will explain the differences. So the first thing is to replace the S1 bundle. Okay, so what did we learn in the courses on algebraic topology? We never assisted that this bundle, this S1 bundle, comes from the fact that KZ2, Einberg-MacLane space, Z2, is the projective space of a Hilbert space. And the projective space of a Hilbert space is at the same time the base space of the classifying space of S1. Okay? That's why a 2 form, once it's integral, gives you an S1 bundle. Now you take a 3 form. Okay? A 3 form has to do with KZ3. But KZ3 is B of KZ2. And so it's a classifying space of PUH, or PH, the same classifying space. So theorem 1 prime, omega integral, 3 form, closed, integral, yields call it big pi M PUH bundle. And then I construct a map from the product Y itself, fiber product, to PUH, which is just given, let's call it psi, which is just given a couple in the same fiber. This defines a map. And here you have an S1 extension. This you pull back, and then you also get an S1 bundle here. And this total space of the S1 bundle you can also interpret as a gerb, as a bundle gerb in the sense of Murray. And on this object you construct what is called a connective structure in the sense of Murray. You have an A, which is a form here. Then you have dA, and dA is T star minus S star of theta. Theta is called a curving. And this couple A with theta is called a connective structure. And d theta minus 2 pi I, pi upper star of omega. This is the exact analog of the first theorem, but the degree goes up. Yeah. H is just any separable Hilbert space. Okay. Separable complex Hilbert space.
Infinite dimensional. Or
infinite dimensional. If you have a finite dimensional Hilbert space and you look at a pH bundle, the DD class is 0. Okay, this is what is called a DD class, omega Tilmann class. The DD class of a finite dimensional pH bundle is torsion. So this is not interesting for us. Omega should not be torsion. I mean, a differential form cannot give a torsion cohomology class. So it should be infinite dimensional. Okay, this is the analog of the first theorem. It's a little bit fast. But, the second theorem, in the second theorem, we have to check what is the analog of the observables. So, the observables of Baez and Rogers is the following thing. This is C infinity n. D goes to omega 1 or n and omega. This is what is called the Lie-2 algebra, and it's not strict Karl Hermann. This is a non-strict Lie-2 algebra. So because the L3 of or L2 of two forms, this is iota is alpha, iota is beta and omega, and L3 is the same. This is L1, for people who know what is the Lie-2 algebra or the infinity algebra. And the theorem says, and I don't want to write it correctly. So, where's the second theorem? This is an isomorphism. The theorem says that the observables act on a certain space of weak symmetries this whole thing calls maybe L point and omega. And the observables are represented on the space of weak symmetries, which is also Lie-2 algebra, which is strict. And here you have a sub-algebra. You have the vector fields on the groupoid. And since this is strict and this is non-strict, the Lie-2 algebra has tendency to need correction. The correction is here. I write it like this. So it's a map from lambda 2 of the whole thing here. And this whole thing is a quasi-isomorphism. This is weak symmetries. And this is a quasi-isomorphism. It's a Lie-2 algebra morphism, which is a quasi-isomorphism. I confess I don't understand why everything gets homotopic in a certain sense, but I can sort of cook it down. And cooking down is, for example, that in a homotopy world, you don't look for isomorphisms of complexes. You go to the homotopy category and so on, and then you look not more for isomorphisms, but for quasi-isomorphism, which means the cohomology is the same. These are very short complexes. So So this is in a certain sense the analog of being isomorphic here. So in a certain sense, when we had these things, we were happy. On the other hand, if you look at the formula, one has the impression it's really hard to calculate something. So on the other hand, I was not very happy. Maybe it's my mistake because I will continue and try to really compute. Try to go to polarization. I think nobody knows really what is a polarization in this case. So it's already getting rather complicated as for my taste. But it's a tentative, which looks extremely analogous. On the one hand, that's the positive side. On the other hand, if you really look at the formula, it's really complicated. So the only example we really calculated was the case that omega has a potential. It was called the P wave, but it's trivial and so on, and you can get better formula, more simpler formula, but okay, so there are many open questions, and I thank you for your attention.